Okay, what are the support reactions for this indeterminate frame? I want to use the flexibility method to determine that. So points A, B, C, and D, you see all the dimensions on here. It's indeterminate because I've got four reactions, a pin at A and a pin at D. Okay, first the cross-sectional properties. Okay, so let's say that it's a 6-inch by 8-inch cross-section. You can find the moment of inertia, 1/81st feet to the fourth. Modulus of elasticity for this material, 4,176,000 kips per square foot. So based on that, I can calculate the flexural rigidity, E times I, and I get this, 51,555.6 approximately, kips times square feet, and A times E, the 1/2 times 2/3 is the cross-sectional area, and then this is the modulus of elasticity. So I've got this as the AE value. Okay, so you got all the cross-sectional properties and material properties. So using the flexibility method, I want to determine the unknown reactions, the two at A and the two at D. Okay, so for the flexibility method, step 1, let D sub x be the redundant. Okay, so the D sub x you see right here, remove that, let that be the redundant. So step 1 is to choose your redundant. And then step 2, the primary frame. Release D by replacing the pin with a roller. Okay, and when I do that, I'll have a figure that looks like this. Okay, now this drawing is not as elaborate as the original drawing. It's just a stick figure. So it's not as elaborate as this drawing, but the dimensions are still true. 12 foot, 8 foot, 18 foot. So I didn't put the dimensions on here, but those dimensions still hold true. The 5 kip load is still there. When I release the pin at D and replace it with a roller, it's going to be pushed to the right. D will be pushed to the right. By how much? Using the virtual work method, I determined that that deflection will be 2.01116 inches. So that is delta sub D sub 0. Okay, so I find that using the virtual work method. Okay, so that's step 2. Replace D by replacing the pin with a roller. I determine the resulting deflection. And now step 3, remove the load. The 5 kip load I'm talking about. Remember that 5 kip load that was at point B? Remove that and apply a unit load at and in the direction of the redundant D sub x. So the 1 kip you see here. Okay, so I'm going to apply 1 kip load to the left. In other words, a unit load to fix the missing redundant. Okay, when I removed that pin at D and replaced it with a roller, remember how it moved to the right? Well, now I got to push it back to the left, so I'm doing that with a 1 kip load. I have to recalculate the reactions at A and D. Okay, so I show the 1 kip load at D, and I show the reactions. I've got a vertical and a horizontal reaction at A, and a vertical reaction at D. Obviously, the sum of the forces in the x direction is 0, so by inspection, I can determine that A sub x is 1. Okay, so that's 1. And then take the sum of the moments about point A to determine D sub y. That's what I'm doing down here. And notice I threw the dimensions on here. Okay, 1 kip at D times moment arm 4. That's the vertical distance between D and A, minus D sub y right here, times a moment arm 18. I find that D sub y is 2/9 kips going down. So here I've got 2/9. Okay, how is that? And then by inspection, taking the sum of the forces in the y direction is equal to 0. I find that A sub y is also 2/9. Okay, so there you have it. I have all the external reactions based upon the 1 kip load being applied horizontally at point D. So now I need to find a delta sub D. Okay, I want to know what this deflection is. How do I do that? Using the method of virtual work. And as I use the method of virtual work, I'll let the system that you see here be both the real and the virtual system. Okay, so using the method of virtual work, remember how to do that? I'm going to set up a table. I've got 3 segments, A, B, B, C, and C, D. I need to determine the bending moment in each of those 3 segments. Okay, so I'm going to set up a table, and I'm going to find delta sub dd using the method of virtual work, with the system that you see here being both the real and the virtual systems. Okay, so first I'm going to analyze this as the P system or the real system. First segment AB. Imagine taking a cut here. Okay, very lightly I draw that. Imagine taking a cut there and analyzing the segment between my thumb and forefinger. Okay, so I'm going to analyze that segment. Okay, watch this. Okay, here's what I'm doing here. I'm analyzing a little segment there. I cut at a distance x up from A. Okay, I take the reactions at A. I've got an internal shear, internal moment. Okay, so examining equilibrium of this, I have, okay, you know how I'm getting this? M is negative x, so that's an expression for the bending moment in segment AB. Notice that the value of this is 0 at point A, and at point B, which is the top of this column. Okay, remember point B, that's up here. That's a distance 12 feet from A, so from A to B, that's 12 feet. So if you replace x with 12, you get negative 12. Okay, so the expression for the bending moment in segment AB is negative x, the value of which is 0 at the bottom, point A, and the value is negative 12 up at point B, which is the top. Okay, so remember that P is the real system, so M sub P will be negative x. I just recopy this equation down here and stick a subscript P to represent the real system. F sub P, that's the axial load in this segment. It's negative 2/9 because I've got that vertical reaction at A. So F sub P negative 2/9. Please remember these 2 equations. I'm going to put these in a table very soon. Okay, and then analyze segment BC. Okay, so BC, that's across the top. Make a cut here. Analyze segment BC. So that's what I'm doing here. Okay, so where does this 12 come from? That carries over from point B. Okay, be careful. Remember that the value of the bending moment is 12 at B. Okay, well that carries over here. Okay, the 2/9, that carries over from the axial load in segment AB. So make sure you know where I'm getting these from. Okay, calculate the moment about point O. Okay, you know where I'm getting all these equations? Okay, so I find that the bending moment, 2/9 x minus 12, the value is negative 12 at B, makes sense. X can reach a maximum of 18 because the distance between B and C is 18 feet. So if you stick 18 in here, you get negative 8. So the bending moment at point C will be, what did I say, negative 8? Okay, then the axial force in there will be negative 1 from the A sub x part. Okay, you see this A sub x down here, joint A. Okay, well that will carry over and turn into an axial load in BC. So F sub P is negative 1. Okay, so M sub P in this case, and it looks like I forgot to write it. M sub P, I can just recopy this. M sub P is 2/9 x minus 12. Okay, how does that look? So remember these 2 equations. I'm going to put all this into a table very soon. Do you know why I'm showing the 12 in a counterclockwise direction? Okay, equal and opposite. So when I analyzed segment AB, I found that M sub P was negative 12 at the top, meaning that it actually goes, well, I'm showing it going counterclockwise, it actually goes clockwise. Okay, so where it meets BC, it has to go in the other direction. Okay, so think about it. Make sure you know why I'm showing it in the direction that I'm showing it. Okay, so now analyze segment CD. So for CD, I have to make a cut in here and determine the equation for the bending moment and also the axial force. So I think it might be easier to analyze CD from the bottom up. Okay, so like I said a second ago, cut it between C and D, and you get this. And I'm analyzing it from the bottom up. So I got the reactions at D. Okay, where I cut it, I call point O, internal bending moment. Equilibrium, sum of the moments about point O is 0. I get that m is x. So the value of the bending moment where x is 0, that is at the bottom, that would be 0, wouldn't it be? And then remember that CD was 8 feet tall. CD was 8 foot, remember that? So up at the top I'll have an internal bending moment of 8. Okay, so m sub p is x, and then the axial load 2/9, a positive because it's in tension. I remember that the dy was pointed down. Okay, so let me highlight everything that I'm interested in. Okay, so I call this an aside because what am I even doing here? I'm doing a virtual work problem in the context of the flexibility method. So I call this aside. Okay, so I need these pieces of information. Okay, I need those, m sub p and f sub p for segment AB. Then I need these. Okay, the -1 and the 2/9 x minus 12. And then I need these. Okay, so now I'm going to organize all these into a table. I'm going to organize all these into a table because I'm trying to calculate. What am I trying to calculate? I'm trying to calculate. Hang on, I'll find it. I'm trying to calculate this delta sub d part using the method of virtual work. Okay, so I'm going to organize all this into a table. So here's my table. I have the 3 segments A, B, B, C, and C, D. Where do I get these values? Okay, so A, B, x is between 0 and 12. Okay, so remember this was 12 feet tall. Okay, and then B, C, x is between 0 and 18. My equations were based on x being 0 at B, x being 18 at C. And then C, D. Okay, that's this here, but at D, x is 0, and at C, x is 8. So I kind of did it backwards there. Okay, so the m sub p part, p is the real, remember that? Okay, so for segment AB, m sub p is negative x. Remember this? M sub p is negative x for segment AB. F sub p, negative 2/9, got it. Negative x, negative 2/9. What about segment BC, m sub p, f sub p. Segment BC, m sub p, f sub p. Did I copy that correctly? I think so. And then for CD, okay, move this up. Remember this from a few moments ago? M sub p, f sub p. M sub p, f sub p. Okay, how do you like that? Okay, so remember that P is the real system. Now I said a little while ago that I would be modeling this as both the real system and the virtual system. This is both the real and the virtual, meaning that I don't have to redo this whole thing. I can actually copy this column into the virtual column, copy this into the virtual column, just like that. Okay, so the m sub p gets copied over, the f sub p gets copied over, real, virtual, real, virtual. Okay, so now what I'll do is use the equation for virtual work to find that unknown displacement. What unknown displacement? What am I doing? What? I'm trying to find this delta sub dd, aren't I? What? Okay, the delta dd is what I'm looking for. So you see here the virtual work equation. Okay, and below that you see the data table that I just showed you. Okay, so the left side of the equation, Q times delta sub dd. The delta sub dd is what I want. Q, that's that virtual 1 kip load. Okay, now watch this. Okay, so I have this. You see the whole thing? Okay, so 1 kip times delta sub dd. Pull out the 1 over EI in the integrand. The EI is constant. You can pull that out. Pull out the EI. So the integral from 0 to 12, negative x squared. So that's MP times MQ. Integrate from 0 to 12. Plus the next segment BC. MP, MQ. So 2/9 x minus 12 squared. Integrate from 0 to 18. Plus third integral from 0 to 8. So I'm talking about segment CD from 0 to 8, x times x. That's what you see here. And then there's the axial load. Okay, so the summation of the axial loads, maybe you can't see that. FQ, FP, L over AE. The AE is constant, so I can pull that out of the summation. Okay, so this first product will be segment AB. So FP, FQ times the length. The length of that segment was 12. Okay, second term, -1 squared, FP, FQ, it's 18 feet long. And then the third one, 2/9 times 2/9, 8 feet long. Okay, so simplify all this. Okay. Alright, so 1 kip times delta sub dd. I evaluate the 3 integrals. I evaluate the 3 products. Okay, so follow the arithmetic. So simplifying this further, I get this, 1 kip times delta sub dd. Okay, and then simplify it further. Okay, what am I doing here? Okay, just look at this part. I know what EI is, I found that earlier. Remember this? The first page. Okay, I found EI earlier. Remember this? 51,556. And the AE was 1,392,000. Remember those values? Okay, so I stick those in. Stick them in. And I find that 1 kip times delta sub dd is this value. See it over here? Okay, so simplify all this. So delta sub dd, 0.0498757095 feet. I'm preserving all those digits because I'm going to need this number for a subsequent calculation, so I want to preserve the accuracy. Converting it into inches, I get this. Delta sub dd, 0.0599 inches approximately. Now, what does that represent? Remember this? This was step 3. Okay, so the delta sub dd represents this displacement. How does that look? Okay, so what do I do with this? What good does that do me? And now step 4 is to repeat this procedure if I have other redundants, which I do not in this case. So I had only one redundant. Step 5, the compatibility equation. Delta sub d0 minus delta sub d sub x is 0. Whether to use a plus or a minus here, I'm using a minus because delta sub dd, that was actually a displacement to the left. So that's why I'm using the minus there. Okay, so delta sub d sub 0, I found that earlier. 2.01116, you remember that? I can't find it now. Actually, I can find it. Back here, step 2, remember? 2.01116. That's delta sub d sub 0. The delta sub dd, I found that a moment ago. 0.5985 inches. The d sub x is unknown. Solve this for d sub x and I get this. So that, dear friends, is the horizontal reaction at D. Okay, so let me find my original drawing. Sorry, I've got papers floating around everywhere. Okay, so let's say 3.360. Okay, I'll round it to 3.360. Okay, so here I have a d sub x 3.360. Okay, how does that look? Can you see this? Okay, so that's the horizontal reaction at point D. How do I find the other 3 reactions? Using statics. Okay, so now I'm going to find the other 3 reactions. And now step 6 would be to finish this using statics. What did I just find? The d sub x part. So the horizontal reaction at D, I found that to be 3.360 kips approximately. Okay, so from that I can determine the d sub y part. Okay, I can take the sum of the moments about point A to find d sub y. I find it to be 2.587. And then the sum of the forces in the y direction is 0, so a sub y must be 2.587 down. So I put a negative sign to indicate that the arrow is going in the wrong direction. And then the sum of the forces in the x direction is 0, so a sub x I can determine 1.640. So there you have it. I've found the reactions for this indeterminate frame. Now this is a book called Rigid Frame Formulas. Okay, so it gives formulas for various configurations. So this was written by Kleinlogel, a very old book. So I want to use a formula in this book to verify the reactions that I just calculated for that frame. Okay, so let me find it. On page 161 of this book, okay, take a look at this here. Okay, frame 46. Two hinged bent with legs of unequal length. So that's very similar to what I just did. Okay, so remember I did this using the flexibility method. Remember this? Okay, so I've got two legs of unequal length. Okay, now take a look at these formulas. I hope you can see this. Okay, so he calls the moment of inertia J. I was calling it I. Oh, that's okay, in notation a little bit different. Okay, so what I have here, length is the distance, the horizontal distance from A to D, that's L. The distance from A to B is h sub 1. Distance from C to D is h sub 2. Okay, take a look down here at the bottom, these coefficients that I have to calculate. Okay, look at these here. I have to calculate these coefficients. K sub 1 is the ratio of the moments of inertia times h sub 1 over L, for example. Okay, K sub 2, similar formula. N, B, C, and big N. Oops, can't see the whole thing. Okay, so I have to calculate these coefficients. Okay, so let me show you what this has to do with the example that I just did. Okay, so take a look at this here. Oops. So a Kleinlogel, page 161, here it is. Okay, so those coefficients I just showed you, here's the frame I was working with. H sub 1 is 12, H sub 2 is 8. Moments of inertia, J. L is 18, 5 kip load. So I calculate those coefficients. K sub 1 was a ratio of the moments of inertia, which will be 1 in this case because the moments of inertia are the same. So this part here just goes to 1. 1. Okay, so I just have h sub 1 over L, so that's 12 over 18. K sub 1 is 2/3. Similarly with K sub 2, again, this is 1. The ratio of the moments of inertia, 1. So K sub 2 is 4/9. Little n, okay, the ratio of h sub 2 to h sub 1, that's 2/3. And then there was a big B that he wanted me to calculate. So I do that here, follow the numbers. I'm supposed to calculate a big C, got that. I'm calculating a big N, 482 over 81. Okay, so where am I? Going back to Kleinlogel's formulas. I calculated these 6 coefficients, didn't I? Okay, so now I'm going to apply this scenario. Do you see this? Okay, so case 46/1. Okay, so the horizontal reaction at A, use this formula. Horizontal reaction at D, use this formula. Vertical reactions, use this formula. Okay, he's probably giving me more than I need here. I just want to calculate the reactions, so I'm going to use the formula for H sub A, H sub D, and V sub A and V sub D. I think that's all I'll need for this example. Okay, so did you get all these formulas? Because I'm going to use these. Okay, the load is P. He's calling it P. So notice that some of these formulas involve P. Right there, right there. Okay, so once again, here's my frame. Okay, I know what all the variables are. I calculated the coefficients a moment ago. Remember that? Okay, so now stick everything into these formulas. Okay, so that's what I have here. Okay, so H sub A, negative P times NC over N. Stick the numbers in there. I'm getting a horizontal reaction at A, negative 1.639. Okay, is that what I got when I did this using the flexibility method? Horizontal reaction at D, P times B over N. Okay, I calculated the P, the B, and the N a little while ago. Or actually, the P is the load, so I calculated the B and the N, but the P is 5. Okay, so the horizontal reaction at D. To calculate the vertical reaction at A and D, I need to calculate M sub B and M sub C, so I'm doing that down here. So M sub B minus M sub C over L. The L is 18. by the M sub B and M sub C. I'm calculating those down here. Okay, and I think I used more than just 3 digits. So I stick those in, and I find that the vertical reactions at A and D are 2.586 approximately. So do these agree with the reactions that I got when I did this using the flexibility method? Well, I sure hope so. Okay, so this is maybe a simpler way of analyzing a frame like this, using a cookbook of formulas, such as the Rigid Frames Formulas book by Klein-Logel.